calculate a variance between person effects due to movement from a conditional growth model to a conditional growth model, this covarying of baseline. So here we have the fixed effects solution, right? So our model solution. And actually you can ignore the bottom because we'll get to that. So what does the model solution tell us? It tells us that negative mood decreases on average over time in 0.05 increments, right? When time is 0, which is now the quit date, baseline negative mood is associated with a 0.5 increase in negative mood. So the worse your mood, your negative mood at the beginning of treatment, the less your negative mood decreases over time, right? So the sample's decreasing as a whole. Those with negative mood at baseline are having a less negative slope, right? Which is less of a reduction. Make sense? Okay. So the only reason I have this here is because I just wanted to remind you guys of what we're trying to do with time. Is we've got here, we're back to showing session 1 through 8. And just to keep in mind that we had this where it started at a certain value, we had a peak at the quit date, and then it went down, right? So just a reminder of that. So here, what we're doing is calculating the variance explained via movement from the unconditional growth model to the subsequent growth model. And we can see that 16.3% of the variance in intercepts was explained by adding negative mood between persons at baseline. Okay? So where did those numbers come from? This is the original number from the unconditional growth model. And then here is that the reduced remaining variance, which is still significant, but is reduced. The fit statistics are also decreased, so these are the originals, so you can compare them right here. And the -2 log likelihood is significantly improved because here's the difference score, so it's big. Make sense? All right, so now we're going to add negative mood by time interaction. So now we have negative mood at baseline, predicting intercepts and slopes. You see? The only difference is we've added it here too. I'm showing you the SAS code, but the logic is pretty straightforward to be able to translate to the other programs. So negative mood, and then time by negative mood. So in this time, we're looking at variance explained in the slopes. All right? And what we get is 7.5% reduction in slope variance between persons. So not totally exciting. And then we also have our fixed effect solution at the bottom here. And what does it tell us? It tells us that the time by negative mood interaction effect is non-significant. It's marginally significant. It does show a somewhat more positive slope if negative mood is higher at the beginning of treatment, but it's marginal, so what do? Keep it, throw it out.
You look at the fit statistics?
Where are the fit statistics? Oh, I guess I didn't. I guess I just threw it out. But, yeah, I must have the fit statistics for this. But, yeah. So, in this case, or I didn't throw it out personally, but in this case, it got dropped due to being non-significant. Just the time by SPOM's interaction and the SPOM's main effect gets kept, right? So covarying baseline negative mood stays, interaction effect gets dropped. Then what happened is, this is Chris Kaler, by the way. So, yeah, not my fault. No, I'm kidding. This new variable is, did you achieve abstinence 1 to 2 weeks post-quit date? Okay? So we have a new level 2 predictor. Okay? A new between-person predictor. We're keeping negative mood, right? But we're now bringing in this measure of essentially outcome, smoking outcome. And then that abstinence by time interaction. So in this example, what's the level 1 model versus the level 2? What's on the level 1 model versus the level 2 submodels? What's on the level 1 model? What are we predicting at level 1? Predicting within person. It's the same. Right? It hasn't changed. Level 1 model hasn't changed. The only thing we're doing now is messing with the level 2 model and predicting the level 1 parameters. Okay?
Why isn't the interaction at level 1? Why is the interaction? I don't get why is the interaction level 2 not 1? Like, wouldn't that interaction be a random effect? Oh no.
Well, this is a between-person effect, right? Whether or not you're abstinent at weeks 1 and 2 post-quit date. I actually don't know if it's like at quit date and 1 week later, or if it's 2 weeks post-quit date.
Okay.
But this is like you either are or you aren't. It's not a time-varying covariate. It's not like, are you abstinent at level 1? Are you abstinent at level 2? Which then you could put it at level 1, because then it would be time-varying abstinence predicting negative mood, which would be actually interesting, but I don't think was done.
Okay.
Yeah, I think it was all subsequent stuff besides the next one is going to be level 2 stuff.
Yeah, so you're going to continue to ask yourself that question for the rest of your life.
Okay.
And the way you answer it is the way Molly just said, which is you ask a second question, which is, does the subject have the same value regardless of which measurement within that subject or within the random unit that they have? And then if you make a mistake put in the wrong place, depending on the kind of modeling you're doing, sometimes the model will just blow up because you've done something that you sort of have one of those things where you're trying to estimate something where there's a constant.
Yeah.
Or you get results where everything in terms of model improvement is exactly 0.
Okay.
So there's all the variances. It's overfit.
Yeah.
All the variances
it's
explained.
Sort of.
There's no variance.
There's nothing to explain.
There's nothing to
explain.
Yeah. Yeah. This is a within. It gets back to that whole using between person questions to answer within person, substantively, to make substantive inferences about within person questions. Okay.
Yeah, actually, one point worth making on the last question of, this interaction 0.07, do you keep it, do you throw it out? One way of answering that question, if it's an interaction where you're trying to confirm a hypothesis that you have, you use the usual rules of if it's not significant, it's not significant. If you're modeling the interaction because it's something that might be a confound in your design, and the most typical example of that is if you have a multi-site study and you're wanting to make sure that site doesn't systematically interact with the rest of what you're looking at. 0.07, you keep site in the model because there's a signal there, it's not significant, but something's going on that you have to account for in the model.
Yeah, my guess is the statistics weren't better as well, if it was non-significant. Because you added a parameter and
Yeah.
didn't get substantial variance explained. So you didn't really, chances are you didn't substantively improve the.
And that was an instance where you were trying to demonstrate that it mattered in understanding the phenomenon, and because you couldn't legitimately claim it, got dropped from the model.
Yeah. I think it speaks to like another kind of interesting point about this process, and which is I think there's a couple of you that are in the Rich Jones RCT class, and 5 times per class, he says, but you're going to do what you originally said, because otherwise you will be accused of p-hacking. P-hacking. He loves that. And it speaks to two kind of I won't even say schools of thought, it's actually like 2 different functions in research, right? So if you got, like, say, an RCT, you've got a set of hypotheses, you test your hypotheses, and you put out your results, and that's the bottom line, right? This is really more a process of exploratory analysis where you're looking to explain what happened. You know, the original, this isn't based on the main effects paper from the RCT. The main effects paper says there was non-significant differences between groups and blah, blah, blah. This paper is about kind of saying, well, why, or learning more about the process of how, you know, smoking cessation affects mood in the context of people who are, because these were depressed smokers. So I call it like being a data detective, in the idea that you're like, the goal is really to explain what happened, and that involves like iteratively kind of putting in things and taking them out and looking at descriptives and saying, and basically like in this process in particular, you know, and this is me as an outside observer trying to kind of think, okay, what was his process? I think the process was like, how do I explain the descriptive data? Or even the predicted data. There's basically like, how do I describe the outcome effects that I see over time? How do you best, you know, put predictors in there to illustrate that process beyond just showing a picture?
So is intercept regressed on week 2 abstinence here?
Do I have the, both intercepts and slopes are regressed on week 2 abstinence here, right? So this is, once you get, my understanding of it is like, okay, so SPOMS is informing the randomly varying intercepts. Abstinence is informing randomly varying intercepts, randomly varying slopes. So that is, so say the level 2 submodel is going to have this term in it, but not like an S in it, because we dropped that SPOM. It's negative mood. I call it negative mood. Does that make sense?
Yeah, except isn't
Is
that
it
like a
wrong?
violation of temporal precedence?
Well, that's where I go back to saying, like, I'm not exactly sure how the abstinence week 1, 2 is coded. So you're saying, because it's not, I mean, this is abstinence and smoking, right? So you are predicting, you are looking at a concurrent lag. But I mean, that's been done before as a sort of, you know, not ideal scenario, right? Because we've got quit date and then 6, 7, 8. And then my assumption is that this is abstinence either at 5 and 6 or abstinence at 6 and 7. That's my guess. I mean, I think the way I've read it in the notes, it's 6 and 7. 1 and 2 weeks post quit date. But in any longitudinal model, we're going to have concurrent lags and then lagged lags, both. Does that make sense? Does that answer the question?
I guess.
Yeah. Okay. Okay, that's that. So what happened here? Fit indices are smaller. -2 log likelihood is significantly improved. These are from the last model. Here's our fixed effects results. Early abstinence, meaning success at quit date, does not impact how negative mood changes over time. So again, we're going to trim this interaction effect. All right? But we're actually not, then we're going to move on to doing something totally different. Like you think, okay, so we're going to carry these two level 2 main effect predictors forward, but we're not. We'll see what we're going to do. All right, so what do we do? First, we added negative mood in session 1 as a control to the growth model. The result was that we improved the variance explained in between person intercepts. We added negative mood at session 1 by time interaction. It was non-significant and we dropped it. We added yes or no abstinent 2 weeks post-quit date by time interaction, main effect and by time interaction. And the abstinent yes or no was significant and the interaction was non-significant drop. So what's the story so far? Baseline negative mood is associated with greater negative mood at quit date. Those who are abstinent 1 to 2 weeks post-quit date show less negative mood on quit date, but do not differ in their slope in negative mood after quit date. Okay? That's the story so far. Any questions? Actually, might speed up a little. Okay, so one question you might ask is like, can we just do a quadratic model at level 1 and be done and forget like with messing around with all this stuff? Which I think is a good question. Right? So this is the difference. This is the first time we've changed the level 1 model. Okay? Just a couple things to keep in mind about quadratic growth is that we think of the slope as the existence and direction of change over time, right? Versus a flat line, versus the intercept explaining everything that happened over time. The quadratic slope is about constancy of change over time. Maybe you could think about it as acceleration or deceleration of change. So here's just a couple pictures of quadratic curves. It is the case, like it can often be the case, I mean, this example looks quadratic, but the question of whether or not we'll be able to pick it up with the time points that we have is sort of an open question, right? You do need more time points, more fine-grained time data in order to be able to pick up a quadratic growth effect. Another thing to keep in mind is just that a positive sign is a convex curve and a negative sign is a concave curve, and that the larger the coefficient, the stronger the curve, right? So those are just a couple comments. This is now kind of just illustrating that we've now added the prediction of the quadratic slope, okay? Intercept, time, quadratic time, error. And so this is where I was like, well, wait till we get to the output and it'll make more sense. We can see now we've got quadratic growth, intercept, quadratic growth, quadratic slope, linear slope, quadratic slope, quadratic slope. So we've added all of this to the variance-covariance matrix. Have we improved the model? This is the information from, this is the value, the within-person residual value from the level 1 model. So not a huge difference. These are the fit statistics from the level 1 model, from the unconditional growth model. Sorry, well, yeah, linear unconditional growth model. So these are better, right? This is not so exciting. So the answer is no, not really. Like, we can't really just make it a quadratic model and be done with it. So then I just put this because it's just, there's a variety of ways of looking at the same thing, right? I think the only, like, the one piece of advice I could give is just like, tell the story that's the most robust, that's the most consistent across methods. Tell the story that looks the most like the picture, the descriptive, you know, the figure. Wait, what else do I have to say about that? So the point of today is considering a number of ways to explain the same data set. We're not done. So far, we converged on a relatively simple story that included 2 level 2 predictors, right? Just those two, just the negative mood at session 1 and abstinence post-quit date, 2 weeks post-quit date. The next thing that Chris did was actually grouped cases by outcome type. Okay, so in order to do this, we drop, it's basically like, okay, this abstinent week 1 and 2 post-quit date, there might be something going on there. Let's probe it more thoroughly, right? So that's why we've now dropped that. We can keep negative mood as a covariate. Actually, no, because we move it, because it's right here. Okay, so specified groups, this is the name of the variable. These are the people that return to, these are the relapsers. Right? This is their negative mood over time. Keep in mind, we're starting at session 1, going all the way to session 8. We've now gained sessions 2 and 3 and 4. These are the people that struggled. They're up here. These are the people that slipped or were mostly abstinent. They're here. And these are the people that are completely abstinent. Okay? So these are the descriptives just telling you the same thing. Relapsers spike most at 5, but they have the steepest negative slope post-5, post-session 5, post-quit date. Strugglers start higher and remain higher. You can look at the picture, right, the red. Mostly abstinent had lower negative mood in the beginning. So I'm just like reading the descriptives, right, summarizing the descriptives. Lower negative mood at the beginning, then the relapsed or struggled, and they remained relatively stable. So they started a little bit lower, and they didn't have that steep of a slope in terms of their negative mood over time. And then the abstinent started low and ended lowest. A second, where are we? Right there. Purple. The healing purple. So, if we put this outcome variable into the class statement, so we're working with SAS here. SAS will dummy code it for us, which is very nice. So we got ID, we've now added outcome type for groups. We've got abstinence, which is the highest group, as the reference. Right, so the other 3 outcome groups are being compared to the abstinent group. And we've got the main effect for outcome group, and then the outcome group by time interaction. This is just saying, okay, what did it do in terms of improving or not improving the model? We've got 13.4% reduction in intercept variance due to outcome type dummy variable. We get an 8% reduction in slope variance between person due to outcome by time. And that's that. Right, so these are comparing. Which one are these comparing to? What would that be comparing to? These are comparing to the SPOMS, just the SPOMS model with intercept and time and SPOMS. Basically where we left off before we added abstinent week 1 and week 2, right? Because we had to drop that variable because it became incorporated into this variable.
So this just compares 2 of the groups?
Dummy codes group 0, 1, and 2 and they're each compared in relation to 3. So they're all being compared to abstainers. All the lines are being compared to this group. That's the reference.
So there's 6 parameters added.
6 parameters added to the fixed effects model. Here are the results. Here are the fit statistics. You see they're actually looking pretty decent, right? BIC is disagreeing, though, that's something to note. But we've added all these terms to the model, right? So it's penalizing us for our model complexity. We also changed the code to, let's see, remove the no test option to get the type 3 fixed effects results, which is basically like an ANOVA telling us like the global, are the interaction effects significant? Is any one of the interaction effects statistically significant versus the main effects? So that's what we've added here in terms of output. And when we look, we have the answer is here, right? So what group is this? This is group 2, and group 2 are the strugglers. So the slope is significantly more positive. Where are we? Here. Sorry, group 1. Group 1, significantly more positive than the abstainers. If we look at the picture, we can see that, right? So, let's see. Okay, so we're moving back in the right direction. I think I said everything I wanted to say. So, any questions on that?
Actually, one comment. Go back to the
Code?
the figure with the forward. That one, the figure with the forward lines. So, for those of you who work with M+, Chris created these groups ad hoc, sort of looked at patterns and so on.
Mm-hmm.
For M+ modelers, this is growth mixture modeling, where you do the group discovery potentially by adding a latent profile set of parameters into the models, and to the extent that you identify profiles, you can then look at the association of those latent profiles with the level 1 and level 2 predictors in the model. So that's one of the things you can do in M+ that you can't do. Well, there's probably a way of doing it in SAS. I believe there's no way possible of doing it in SPSS. And Rich probably knows a way of doing it in R.
So you would run a latent class
can-
analysis and like spit out something
Well,
and
there's
then
a
use
class of models in M+ called growth mixture models, which are explicitly designed to address this problem.
in one step.
Depends
One.
what you mean by one step. In
One model.
One model, which is explicitly addresses the question of, are there discernible patterns that you can model within the data that are associated with the patterns of function over time. And that's actually a big, if you go to the Oregon Social Learning Center, OSLC, out in Eugene, you'll find dozens of people doing growth mixture modeling out there. It's kind of like they're junkies about that.
But it's what is going on,
Mm-hmm.
right?
Yeah.
You know, I mean, this is what's going on in an RCT.
Yeah.
It's not one type of person changing in one type of way. You know, like
Yeah.
this is
Yeah.
something I found that I thought was nice. Right? It's like this is our world.
Yeah.
This is our world.
Yeah, it looks like a trash can, doesn't it?
It's like a, you know. I don't show the findings for this, but I wanted to make sure I covered it. So this is going to your piecewise models, I think. So this is a discontinuous change model, which is what Singer and Willett refer to it as. And so I'm not showing you the output, but I wanted to show you the coding, right? So we've got case ID 200. We've got time 0 to 7, so we've got all our time points with baseline. We've added baseline. We've got baseline at 0. We've got quit, yes or no. Has it been quit date, yes or no? Right? So at 1 starting when the quit date started. Baseline 1, 2, 3, 4. No, this must be session 1. Yeah, because there was 8 sessions. So session 1, session 2, session 3, session 4, session 5, quit date, right? And then is it post quit date and allowing for a linear slope post quit date, right? So we could then, so this is, getting rid of outcome groups and just treating this quit date as an event that might change the form of time post-event, right? And so by coding the data in this way, that would allow us to do that, to test that with interaction terms. These don't have interaction terms, but so this will be some starting syntax for that, but you might add outcome by post-quit date interaction. Does anyone work with these discontinuous change models? Where you're essentially, it's like event-based coding. You're looking at a particular event as a way to, rather than this idea of a quadratic slope, just saying, okay, no, there's a peak at session 5. That's what's going on, right? Does anyone do this? Yeah.
I mean, with latent growth curve modeling, yeah, there's these transitions in adolescent development, where you, for instance, go from middle school to high school, and you might want to separately plot curves for each of those scenarios because you expect different patterns of growth given different scenarios or environments.
And when you do those, do you do like coding like this in the data first? So is there's something in M+ that you can do to just do it automatically, kind of?
Yeah, I just don't assume a 2-level model. I just plot 2 growth curves.
And then, but how do you know where the time, like what the point is? Or you just say, tell me about 2 growth curves.
So first, like, you have your time points, where you have variables representing the time points, and you just make sure that the transition is centered. So that whatever time point is, the transition corresponds to that same variable for each participant.
Okay, that makes sense.
Yeah, there are a bunch of ways of doing it. In M+, you could define I1, I2, S1, S2, and I1 is only for the first part, I2 is only for the second part.
And that intuitively maps on to what we've been talking about, right? I1 and I2, S1 and S2.
Yeah. So actually, we were just meeting with genetics colleagues yesterday because we have a study, 3 to 5-year-olds, a couple time points where we have genetics material. Looks like we're getting funded for a follow-up when the kids are 8 to 10, and we're talking about measuring obtaining genetic material at multiple time points with the intent of looking at rates of methylation associated with contextual adversity, with the hypothesis that methylation rates will be higher in early childhood than middle childhood, which is consistent with sensitive period, and everything that happens in infancy is more important than everything else in life, which is the conceit of us infancy researchers. But it's exactly the same thing, that the rates of growth are different at different time points, and there's we have a 5-year gap. But even if there weren't, that same hypothesis would have one of these discontinuous growth models.
What's methylation?
The degree to which contextual factors affect the genome and ultimately affect gene expression.
Oh, okay. Because I thought you were saying like a specific type of outcome, but it's the nature of an outcome.
No. Right.
Okay. All right. All right, so we're just about done. I wanted to show you where Chris ended up, which is with like a ton of information is where he ended up. But this is like, that's what makes this such a great teaching example. So negative mood, depressive symptoms, And major depressive episodes were examined in 179 smokers with a history of major depression in a trial comparing standard smoking cessation to a CBTD. Early lapses were associated with relatively large increases in negative moods on quit date. Mood improved in the 2 weeks after quit date among those returning to regular smoking, but not among those smoking moderately. Continuous abstinence was associated with short and long-term reductions in depressive symptoms. Major depressive episode incidence during follow-up was 15.3%. It was not associated with abstinence. So 3/4 of those findings we talked about how we got there. We didn't talk about the major depressive episode incidence. And then this next one, the treatment interaction. So that's the end of the story. And I don't know if those are actually the ending fit statistics, but they look nice and small, so I put them there. Any questions or comments, examples from your own work? Okay, all right, until
Thank you.
next time.